Back. In this video, we're going to go over separate chaining. So the idea behind separate chaining is that if we have two elements that basically collide at the very same spot, what we're going to do is we're going to add the second colliding element to the very front of the bucket that it basically hashed to. So the idea here is originally in this bucket, at bucket 1, we had the value 1. And then what we try to do is we try to find a spot for 81. And then we say, oh, okay, 81's going to a spot that's already occupied by the value of 1. But all we're going to do is make a simple insertion of the 81 into the very front of the bucket here. So the cool thing about this is that the load factor for separate chaining could be much higher than the load factor for open addressing. This will lead to less rehashing needing to be done over time. So this works well for large data files here. The downside to this is it uses two data structures, and depending on how you implement it, can be a little bit tricky. So there's also a kind of cool graph here that we can take a look at. So as you guys can see, these are various load factors for chaining and linear probing. So as you guys can see, if we have a very large load factor for linear probing or our open address table, it can take a very, very long time for us to actually find an element or an open bucket here. So that's pretty bad as far as things go. But as you might have noticed, separate chaining is just kind of this nice linear path here. So I mean, it gets a little worse over time with the larger and larger load factors, but it can definitely take a larger load factor here. So, okay, let's actually take a look at the implementation of this. So, default capacity just represents the size of the size of our buckets, or the collection that's storing all of our buckets, which is going to keep 10 buckets. Our load factor is going to be 2.0 in this case, or 200% of the number of buckets that we have. Size, once again, keeps track of how many elements we have. And our structure that we're using is I'm using an array list. And this array list, each one of its buckets is going to be an empty linked list with strings. So the idea here is when I set up the separate chained hash table, I just set the size to 0, and I just make the table a new array list of linked lists of the size of the default capacity here. So an insertion method, what it's going to do, it's going to find the appropriate hash spot, and then we're going to call the linked list method for add, and we're going to add that value to our linked list. And then we're going to increase our size, and then if our load factor is ever breached, we rehash. So deletion, all we're going to do is we're going to say, okay, from our table, let's get the appropriate bucket where this value hashed to, and then let's call the linked list's remove method on that specific spot. And then let's see, let me make sure the index of value. Yep. So what it does here is what we're going to do is we're going to call remove on the linked list's appropriate value, if we can find it here. So next thing, our search method is pretty simple as far as things go. Fortunately, since the linked list class is already implemented for us, what we can do is we first get the original hashing spot here, so we find the appropriate bucket, and then what we try to do is we try to find where it is in our linked list. So for that, we call our get method again, which gets the appropriate bucket. And then after we get the appropriate bucket, since we know that we're dealing with a linked list at this point, we just get the index of the string value that was passed in. So no sense, no point trying to make your own linked list class when somebody's already made it for you. So no need to reinvent the wheel here. Our hash function, it's very standard. This is taken straight from Mark Allen Weiss. I mean, it uses the entire string here, and then we happen to use a little bit of Horner's rule, polynomials, to reduce the number of calculations we need to do, and we use every single character here in our hash function. So our rehash is pretty simple and pretty standard. We just keep track of our old table, set it equal to our original table. Then our original table gets doubled in terms of size, and then we loop through our old table and each of the elements that it stores in it, and we basically hash everything. So what we need to do is we need to go through each individual linked list, and we need to rehash each individual node. So the reason why we have to do that is because it's entirely possible that our linked list chains are going to be broken when we rehash, because some of the nodes that might have hashed to the same spot before might be hashing at different locations. So yeah, this is just a simple implementation of separate chaining, and I hope you guys found it useful.